Okay. So I think I want to skip the MVT for now and go over the next part. So, because I feel that's harder. Because I think most of the questions on MVT and roles, it's what do you call it? It's pretty straightforward. So, yeah, okay. Okay. So, if you recall, right, how did you all find, if I give you a function, a continuous function on a closed interval, how do you find the absolute maximum and minimum? Like, I don't know. On like 1 to 2. How how would you find the absolute max and absolute min? Anyone? So, does anyone remember extreme value theorem? Yeah, you find critical values and test the boundaries, right? But now let's say I'm not on an interval, right? So you can still find local max and local min, right? And picture-wise, they correspond to when the derivative 0, right? Like these little lumps, sort of. Or like when derivative doesn't exist, right? So let's say I find C where f prime of C is equal to 0, right? So I guess your first question is it local max or local min? Local min or neither? Yeah. So and there is a case where it's neither, right? So that's the first thing we're gonna try to see. Yeah. And it's gonna be called the first derivative test. It looks complicated, but it's really not that bad. Derivative test. Suppose C is a critical number. Sorry, critical number of a continuous function f. Right. A, if f prime changes from positive to negative, let's see, then f has local max at C. B, if f prime changes from negative to positive, at C, then F has local min at C, and there's the third case, right? If it doesn't change at all. So if F prime is positive left to left and right of C, or vice versa, negative to left and right of C, there is no local max. Is no local max slash min at C. Yeah. So this is pretty simple, right? So let's sort of see why, right? The first part, I'm at the top of the, let's say this is the point C, right? It's the derivative of 0. So if to the left of C it's positive, was my function increasing or decreasing to the left of C? If the derivative before C is positive, locally, of course. But yeah, it was increasing, right? So something like this, right? Now, after C, it's negative. The derivative's negative, so it's decreasing, right? And you see from here, you get like a hill. As opposed to here, right? For this, if this was the point C, if before C you were negative, that means you were decreasing this to C, right? So you're going like this, right? And then after C, you're positive. So you're going back up, right? So you're, in this case, you're sort of like in the bottom of a hole. And this is, you know, if you're positive both left and right, is not possible. Like the classic example would be like f of x is x cubed, right? Like here, right? Derivative is 0 here, right? Derivative at 0 is 0, right? I mean, in this case, you can just check it, right? 3x squared f prime of 0 is 0. Yeah. All right. So in this case, right, there's no local max, local min, because the derivative is positive before, right? Before 0, it's increasing, and after 0, it's also increasing, right? So we're in like the first case. Okay, everyone good so far? Yeah. Okay. Now, of course, the if the derivative tells you something about your function, right? Then the second derivative tells you something about f prime, right? Because the second derivative is just f prime prime. Is the slope of the first derivative. But then your question is what's relation between f double prime uh, and f, right? You know relation between f double prime and f prime, right? This is just derivative of, if you like, uh, this thing is just derivative of f prime, right? So it's just the slope of f prime. But what about the f double prime and the original function? So for that, we have to think of concave upward. I'll write smiley face. Upward. Think smiley face. I don't know how to spell this. Smiley face. Ren, but the actual definition is ren f above all tangent lines. And concave downward. So let me just say think frowny face. Ren f below all tangent lines. So right, if you just think of the smiley face, right? Like if you just ignore the eyes, right? Like if you take any tangent line, right, you're going to notice the tangent lines below your function, right? No, like for any point you take here. And then for a frowny face, right, if you ignore the eyes, like if you take any tangent line, it's always above your function, right? So that's what we mean by concave up and concave down. So okay, so now there's something called concavity test. So it turns out that, if your second derivative is positive on interval I, then graph of f is concave upward on I. Yeah. So it's sort of looks like a not maybe it might not be the whole smiley face, but it's part of that smiley face, right? And B, if f double prime of x is less than 0 on interval I, then graph of f is concave downward on I. Yeah. So this is just definition, but a point P on y equals f of x is inflection point if f is continuous and curve changes concave down to up, or the other way. So changes concave down to up or up to down. Yeah, so a classic example would be something like this, right? Smiley face to frowny face, right? And this would be like your inflection point, right? Because after this point, you become frowny, right? And before it, you're in the shape of a smiley face. Yeah, so that would be like an inflection point, picture-wise, of course. Everyone good with this so far? The theory, if you accept this, does everything make sense? So, okay. So if you don't like first derivative test, they have another test for you to use. It's called second derivative test. So suppose f double prime continuous near C. If f double prime of C is 0, or sorry, f prime of C is 0. And f double prime of C is bigger than 0. F has local min. At C. B, if f prime of C is 0, f double prime of C is less than 0, then f has local max at C. This seems difficult, but really, if you just think about happy face, smiley face, it's easy. So what does this tell you? The first part. It tells you, are we in a happy face or frowny face? If f double prime is bigger than 0. Good. So it looks something like this, right? Now the point could be anywhere, right? It could be like here, 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 here. But this thing tells me it has to be here. Yeah. The f prime of C being 0, right? Because I know that, it's only for flat. The tangent line has to be flat. So this thing tells me where on the smiley face I am. So this thing tells me it's at the very bottom. Same thing here, right? This thing tells me it's frowny face, and this thing tells me I'm at the top. Yeah. So I'm a local max. And yeah. Okay. Everyone understand the theory. So we're gonna get into exercises. It might be a bit hard for people who are learning this the first time. But yeah. Okay. So this this question comes quite often. So this thing is they give you the graph of f prime, right? So you should be careful. 0. Let me see if I could graph this correctly. 4, 5, 6. Yeah. So these type of questions come off up a lot. Oh, by the way, I'm guessing the other students had a different homework than you, because when I looked at homework 7, there were no related rates. I guess that's a good thing because I think a lot of students don't like related rates. Okay, so the graph looks like this. So at 4 is the top of the hill, bottom of the hill, something like this, or if you like. So this is the graph of f prime, right? So on what intervals is f increasing, decreasing, uh, at what values of x does f have local max? And then same question, local min. All right, so let's try to answer, this is part A, part B. Let's try to answer the first question of part A. So on what intervals is f increasing? So again, you want to they give you the graph of f prime, right? And they're asking you about something about f. So you want to translate it to something about f prime, right? Yes. So f increasing is the same as f prime positive, right? So what intervals is f prime positive? By the way, yeah, let me just erase this. It stops at 6. So yeah, 0 to 1 and 3 to 5. Yeah, we don't really care about the endpoints. You could do open, close, whatever you like. So this thing is 0, 1, union 3 to 5, right? Because it's above the x-axis, right? Okay, so on what intervals is it decreasing? So this is when the derivative's negative, right? And we are negative here and here, right? So again, this is what, 1 to 3, union 5 to 6. All right, great. Let me erase these red things. No. Okay, so let's do part 2. At what values of x does f have local max? So what's your first? What's the first thing we should do for local max? If I give you a function and you want to find local max and local min, right? What do you do? So how about this? Let's go back to here, right? What's the first sentence below first derivative test? So what should I be looking for? Yeah, I'm looking for when the derivative is zero, right? That's what critical number is. Agree? In this case, I drew the derivative, so of course it exists. So really, critical number in this case is, wherever, remember, critical number is whenever derivative is zero, right? So where is it zero? Okay, good. So let me just do 1, 3, and 5. So these are the spots where the derivative is zero. Now, what do I need to check? Let's go back to first derivative test. So I need to check, before, what's the sign, right? Before 1, after 1, before 3, after. So let's check the sign, right? So before 1, is my derivative positive or negative? Positive, good. What about before 3? By before 3, I mean like after 1. After 1 and before 3, if you like. So yeah, negative. And you can see, right? 3 to 5 is positive. 5 on is negative, right? So at 1, am I local max or local min? So again, think of increase, decrease, right? So before 1, I'm increasing the 1, and then after 1, I'm decreasing. So it's local max, right? Because that would mean 1 is at the top of the hill, right? So local max, right? I'll just write like this. What about 3? Sorry, there might not be a comma. So at 3, I'm going down to 3, right? Because I'm negative before. And then after 3, I'm going up. So is that local max or local min? Local min, good. And what about 5? Good. See, you all got it. Okay. So let's continue. I'll do one more. This one actually has way more questions. I don't know why, but like it's super hard to draw. So this time, I won't give hints. I'll ask all of you for the answer. So, see. So it looks like this. Goes down a little at 2. Goes back up a little at 3. Goes down to the axis at 4. Goes down to 5. This is smooth, yeah, not sharp. 6. Up at 7. Down at 8, and all the way down. So this is the graph of. I mean, to make it easier, we can just, whatever. So this is the graph of f prime. Yeah. So for the purposes, let's just this time, you know, uh, what do I want to do? Yeah. Okay. Let's just say it goes off to, goes off like that. Yeah. It starts at like 0, goes off to infinity, if you like. So on what intervals is f increasing? I don't think it matters much, but just to be pedantic. So let's just do increasing. So what intervals? So let's say it stops here. Yeah. So domain is like 0 to infinity. Zero to 4, 6 to 8, right? Good. All right, part B, and that's because again we're above the x-axis, so we're positive, right? Now part B, same question. At what values of x does f have local min slash max? So let's do local max, local min. So again, what are my critical numbers? Good. So I'll let you think in this case. So at 4, I go from positive to negative, right? So what am I? Good. Now what about 6? I'm negative before 6 and I'm positive after 6. So good. And what about 8? So positive and then negative. So hope you know by now. Good. All right. Now, new question. On what intervals is f concave up and concave down? So again, let's go back to concave up, concave down. Yeah, let's go back to that thing. What does it say, right? So f is concave up when your second derivative, if you look at concavity test, is when your second derivative is positive and second derivative is negative, right? For concave down is negative and concave up is positive. So knowing that, right, this is basically asking Ren is f double prime positive, Ren is f double prime negative. So from the graph, Ren is f double prime positive. So if you like. So you need to relate f double prime with f prime. So how is f prime and f double prime related? Again, because they give you the graph of f prime. So how is f prime and f double prime related? Well, seem confused. How about this? How is f prime and f related? Can any of you tell me that? Yeah, f prime is the slope of f, right? Slope of f, right? But f double prime is just f prime prime. Yeah. So this is the slope of f prime. Everyone agree? Yes. Okay. So it's just asking, Ren is the slope of f prime positive. So can you give me the intervals for that? So what's the first interval? Good. And then Good. 2 to 3. And then I think one more. So yeah, 5 to 7. Good. And then the what do you call it? It's concave down from, let me see, 1 to 2, right? I'm decreasing, and then 3 to 5, and then I'll just put 7 to infinity. Okay. Is everyone clear on this? Yes. So I know it's a bit hard, like it's kind of tricky, but you have to just draw a chart and like relate all three of them. Okay, so this is just graphs, right? So let's see how it's in practice when I give you an actual function, right? So a so this is, I think both is part of your homework. Like your homework has like graphs, and like also they give you a function, and then you need to find stuff like these. So intervals where f increasing or decreasing. So no more graphs now. So B, find the local max / min values of f. Find intervals of concavity. And inflection points. So let's say f of x was this. All right. How do I solve part A? What should I do? Yeah, right. Again, f increasing means derivative positive, right? So let's take derivative and check when is positive, when is negative, right? 4x cubed minus 4x, right? So this is 4x. So let's figure out when it's 0, yeah? Because that'll tell me, because once you're above 0, below 0, that means you're positive or negative, right? So from here, you get x equals 0, x equals 1, x equals minus 1, yeah? So these are my critical points, right? Critical numbers, if you like, critical numbers, right? So again, critical numbers is when you set derivative equal to 0, right? And now I use the first derivative test. So let's figure it out, right? I don't know why I wrote this so big. So all right, take a point before -1. Is f prime positive or negative there? Like, pick your favorite number. Like, I don't know, -2. Plug it in here. You don't need the value. You just need to know, is it positive or negative, right? So maybe plugging it into like this thing's easier for some people. So if I plug in, if I plug in like -2 here, is it positive or negative? Yeah, negative, right? Yes, negative. So let's put a negative sign here. All right, now pick your favorite number between -1 and 0. Let's say -1/2. Is it positive or negative? Okay, so 4 times negative a half is a negative number. So let me just do it for you. And what's is negative a half squared minus 1? Is that positive or negative? All right, what's negative times negative? So again, you don't need to know the value, right? Nobody's asking you to actually solve for the value. So from here, a negative times negative is positive, right? All right, now same exact thing. Pick your favorite number. Pick your favorite number before between 0 and 1, right? So let's say a half, right? 4 times a half, positive number. A half squared minus 1, negative number, right? Positive times negative is negative. And if you like, pick your favorite number after 1, like I don't know, 10. Yeah, 4 times 10 is positive. 10 squared minus 1 is positive. Yeah. Okay. So knowing this, let's answer the first question. On what intervals is f increasing? Yeah, just look at what the plus signs are, right? Because f increasing means derivative is positive, right? So let me write like right here. Increasing -1 to 0 union 1 to infinity, right? And decreasing is wherever the negative is, right? Negative infinity and -1 union. Okay, so from here, right, find the local max and min. So for part B, we're almost done with it already, right? These are the critical numbers, right? And from the chart, let's look at -1, right? So from here, this chart right here, before -1, I'm decreasing, right? Because it says I'm negative, right? So before -1, I'm decreasing. After -1, I'm increasing. So what am I? Good. Okay, so from here, same thing for 0, right? So before 0, I'm increasing. After 0, I'm decreasing. So what am I? So again, I'm looking at this and this now. Yeah, and hopefully you know this thing is a local min. Yeah. All right, so we're pretty much done with 2 of them. Let's do part C. So let's find interval. So how would I find intervals of concavity? Good, right? It's when second derivative is positive or negative, right? So let's take this. Let's take the second derivative. Let's find the second derivative. So it's just derivative of this thing, right? So this is what 12x squared minus 4. Yeah. So let's set it equal to 0, right? What do I get? X squared equals 1/3. So x is plus minus √3 over 3. Yeah. So same exact process. √3 over 3. Negative √3 over 3. So take a number before negative √3 over 3, right? I mean, negative √3 over 3 is a number smaller than negative, I guess bigger than -1, right? So plug in like -5 if you like. So if you plug in -5 to this thing, is it positive or negative? Good. All right, so between, hopefully you have your favorite candidate, right? The best number to choose when you have if you're squished between a negative and positive number is 0. So if you plug in 0, do you get a positive or negative number? Yeah. What about after? Right. If you plug in 5 now, it's positive. Okay, so let's answer the question. When am I concave up? Yeah. So I'm concave out wherever the plus signs are, right? There's a negative sign here. Union √3/3 to infinity. And then I'm concave down wherever I'm negative, right? So same exact thing for inflection point, right? These are the candidates for your inflection point. So inflection point is if you change concavity, right? So if you go from concave up to concave down or concave down to concave up. So in this case, is this the case for these 2 points? Do I change from like up to down and then or down to up? Yeah. So my inflection point is this is the annoying thing. It's a point, right? So you need to give the y value. So let me just say, you know, I don't want to calculate this right now, but it's f of negative root. You plug into your original function, right? So these are 2 points. So right. So if it was something like this, right, where it was plus plus minus, right, for like AB. So if it was like A to B, right, if it was like plus plus, right, then this would not be an inflection, right? B would still be inflection because you're going plus to minus, right? You're going concave up to concave down. But here it's concave up to concave up, right? So you see, if it was something like this, then like only BF of B is like inflection. Yeah, okay. Okay, it won't let me write, but okay, is everyone clear on this? Yeah. I think this is like question 10, 11 on your homework or something. Okay, so I'm just gonna end by, maybe I guess I do have time for MVT. To maybe just talk about the statement of MVT. So mean value theorem, if you don't know what it is already. So 1f continuous on closed interval AB, 2f differentiable. So this is a bit stronger, right? On open interval A to B. So unlike the extreme value theorem and intermediate value theorem, this one requires f to be differentiable, right? So if you remember intermediate value theorem and mean value theorem, intermediate value theorem and extreme value theorem only required continuous, right? Then there is a number C in AB such that f prime of C is f of B minus f of A over B minus A. So picture-wise, it's this, right? If I had like a function here, right? A to B, what is this thing? If this is my f, this thing is just the slope of this line, right? Of the line that connects these 2 points, right? The point B, f of B, and A, f of A. You all agree? So the right-hand side is just the slope of this line, the line that connects these 2 points, right? So mean value theorem just says there's some point in between that attains that actual slope. So yeah, I don't know where, but there's some point where the derivative is actually the slope of this line. Yeah, so that's just the geometric intuition. Rolle's theorem you don't really need to know because it's a corollary of mean value theorem. So, but they do ask you on rolls, but A to B to F differentiable on open interval AB. And 3, they require f of A is f of B. Then there is a number C in AB such that f prime of C is 0. So you see here, Rolls is basically saying there is a critical number, right? So there is basically saying there has to be a point where there's a local max or local min, right? Supposedly. But or like maybe not local max, local min, but there's a point where you're 0. So can anyone tell me, just before we go, why Rolle's theorem is a corollary of MVT? So if I assume f of A equals f of B, what's the value of this? What's the value of the numerator? If yeah, so you see Rolle's theorem is just MVT with a special case of it, right? Where you're assuming the numerator is 0. I mean the f of B equals f of A just means numerator 0. Yeah, so I think the questions that on the WebAssign that test you on these theorems is pretty straightforward. I feel the hard part is the thing I went over previously, like concavity and increasing, decreasing. But yeah, so next time I'll probably go over a bit of curve sketching and maybe like optimization. Yeah, this homework's long, by the way, so there'll be stuff not covered yet. Okay, I will see you all next Tuesday then.